Chapter 4. Solving systems of two linear equations or inequalities in two unknowns. In two variables of two variables. Section 4.1, solving systems of linear equations by graphing. Okay. So first off, let me tell you what a system of two linear equations looks like. So a system of simultaneous linear equations. So one linear equation in two variables, well, I can write it as, let's say, in standard form, ax plus by equals c. And let's suppose I have another line, dx plus ey equals f. And so this system together is called these two lines together is called a system of simultaneous linear equations. A solution to this system will consist of an ordered pair, let's say xy, such that when I substitute x into each equation and y into each equation, both equations are satisfied. So let's do some examples. Let's say on page 152. Let me do problem number 1. And so I have the first equation, let me call it R1, 4x minus 3y equals 6. And I have the second equation, let's call it R2, x plus 2y equals 7. And suppose I have some ordered pair 3, 2. In exercises 1 through 18, identify whether the indicated ordered pair is a solution to the given system. So let's check. Let's check if the point 3, 2 solves the first equation. And so wherever we see an x, replace x by 3. Wherever we see a y, I replace y by 2. And check if this solves the equation. So 3 times 4, 12 minus 6 is indeed equal to 6. Good. Now let's check if the point 3, 2 also solves the second equation. And so let's replace x by 3, y by 2. Is 3 plus 4 equal to 7? Yes. Therefore, yes, 3, 2 solves the system. So yes, 3, 2 is a solution to the given system. Let me do problem number 3. 3x minus y plus 4 equals 0. Maybe I'll call that R1. R2, 2x plus 5y equals 3. So it asks, is the point negative 1, 1 a solution to the system? So let's check. So first let's check if 1, negative 1 or negative 1, 1 solves R1. And so is 3 times negative 1 minus 1 plus 4 equal to 0. Now let's check. Is negative 3 minus 1 plus 4 0? Yes. Next, let's check if negative 1, 1 solves the second equation, R2. Is 2x plus 5y equal to 3? Is 5 minus 2 equal to 3? Yes. Since the ordered pair solves both the first and the second equation, then yes, negative 1, 1 is a solution. Let me do problem number 5. Let me just check. Okay. Let's call the first equation R1. Negative 2x plus 5y equals 1. Call the second equation R2x minus 4y equals 3. So I want to check if 2, negative 1 is a solution. So let's first check if 2, negative 1 solves the first equation. Negative 2x plus 5y is that equal to 1? So let's check. Negative 4 minus 5 is not equal to 1. So automatically I know it's not a solution. So no, 2 negative 1 is not a solution. It has to solve both equations. Since it doesn't solve one of them, then it's not a solution to both of them. Let me do problem number 7. Call this R1. 3x plus 2y equals 0. R2, 2x equals 3y minus 5. And so, is negative 2, negative 3 a solution? So let's check. If negative 2, negative 3 solves R1. So is 3x plus 2y equal to 0? Is negative 6 minus 6 equal to 0? No. So no, negative 2, negative 3 is not a solution to the system of simultaneous linear equations. Let me do problem number 9. Four x plus 3y equals 15. Let's call this R2. Problem 9. X minus y plus 5 equals 10. So it's asking, is 0, 5 a solution to this system of equations? So let's check. If 0, 5 solves R1, is 4x plus 3y equal to 15? Is 0 plus 15 equal to 15? Yes. Now let's check. If 0, 5 solves R2. Is x minus y plus 5 equal to 10? Is 5 minus 5 10? No. And so, since this doesn't solve, this ordered pair doesn't solve the second equation, then no, this is not a solution to the equation. So no, 0, 5 is not a solution to the system of simultaneous linear equations. Let me do problem number, question. Oh no, don't say that. Let me do, let me do problem number 11. Call this R1. 3x plus y equals 5. Call this R2. 2y equals 10 minus 6x. And I want to check if 1, 2 is a solution to the system of linear equations. So first, let's check if 1, 2 solves the first equation, R1. And so, is 3x plus y equal to 5? Is 3 plus 2 equal to 5? Yes. Let's check if 1, 2 solves the second equation. And so is 2y equal to 10 minus 6x? Is 4 equal to 10 minus 6? Yes. Since both equations are solved, then yes. 1, 2, the ordered pair 1, 2, is a solution to the system of simultaneous linear equations. Let me do problem number 13. R1. 2x minus y equals negative 4. Second equation. 2x minus y equals 1. And so they ask, is 0, 4 a solution? So let's check. Check if 0, 4 solves the first equation. And so is 2x minus y equal to negative 4? Is 0 minus 4 equal to negative 4? Yes. Let's look at the second equation. So let's check if 0, 4 solves R2. Well, is 2x minus y equal to 1? Is 0 minus 4 equal to 1? No. And so no, 0, 4 is not a solution to the given system of linear equations. Let me do problem number 15. Three x minus 2y equals 6. 9x minus 4y equals 24. And so, is 4, 3 a solution? So let's check. So first check if 4, 3 solves the first equation. Is 3x minus 2y equal to 6? Is 12 minus 6 equal to 6? Yes. Let's check if 4, 3 solves the second equation. And so is 9x minus 4y equal to 24. So is 36 minus 12 equal to 24? Yes. And so yes, for the ordered pair 4, 3 is a solution to the given pair of simultaneous linear equations. Let me do problem number 17. 2x, let's call this R1, 2x plus y equals -1, call the next one R2, x plus 2y equals 4. And so is -2, 3 a solution? Okay, so let's check if -2, 3 solves my first equation. So let's check if -2, 3 solves the first equation. And so is 2x plus y equal to -1. Is -4 plus 3 equal to -1? Yes. Now let's check if -2, 3 is a solution to the second equation. And so is x plus 2y equal to 4? Is 6 minus 2 equal to 4? Yes. So yes, -2, 3 is a solution to this system of equations. Okay. So that's all nice and fine. So now we know how to check if a particular point is a solution to the system of simultaneous linear equations. The question is, well, how do you solve it? So there'll be several techniques that we'll be going over. So let me list them. So these are the techniques to solve systems of linear equations. Okay. So the first will be the graphing method. And well, we'll be doing that in this section. The next technique is substitution. And we'll be doing that in the next section. By the way, we'll also be doing this again in a later chapter. I think it's chapter 8. But in there, it'll be more than 2 equations. Next technique elimination. And so for elimination, we'll do that in section 4.3. Next, the matrix methods. Actually, we won't be doing that. This is done in Math 245, Math 259, Math 260. So those methods will not be covered in this particular course. Next, determinant. Solving by determinants. And that's going to be in section 12.3. Oh, so it's chapter 12. So in chapter 12, we'll be doing these techniques, go over again, but it'll be in the case of looking at 3 or more variables, 3 or more equations. Okay, so let me tell you about the graphing method. Okay, so suppose I have some coordinate system. Then, if I have some equation, ax plus by equaling c, I know that that's just the equation of a line, and any line in the plane can be put into that form. So there's some line in the plane that has that equation. Similarly, if I have another equation, let's say dx plus ey equals f, then, well, I have another plane in the line. It turns out that the solution will just be this point of intersection. And so these numbers that we were finding above and checking if there were solutions, we were actually just finding the point of intersection of these lines. And so let me give you some terminology. Intersecting lines. Suppose I have 2 lines in the plane. Call this L1 and L2. And suppose that this is relative to some coordinate system. Then, if these 2 lines are such that, and suppose that M1 is the slope of the first line, M2 is the slope of the second line. If these 2 slopes are not equal, then there will be one point of intersection. Between these 2 lines. And so that means that this system will have a unique solution. This system will be called a consistent. It's also independent. Usually, I'll just say consistent system. It's understood that it's independent. Next, suppose I have the case of parallel lines. So suppose I have two lines in the plane such that they never intersect, and suppose that this is relative to some coordinate system. So let's call this L1 and L2. Let this be slope M1 and this be slope M2. Then these two lines will be parallel. So this was the case here of intersecting lines, meaning that these two lines were not parallel. Here I'm looking at the case of two lines being parallel. And so I'll actually have to split it up into two pieces. So these are parallel lines, but they're not the same line. So they're parallel lines, but let's assume that they're not coincident. Okay. So in this case, the two slopes are the same, but they're different lines. So let's say that their y-intercepts are different. Of course, if they're vertical lines, then we'll have to say their x-intercepts aren't the same. Then this has no solution because there's no point of intersection. So this has no point of intersection between these two lines. And so that means that we have no solution. The number of solutions is 0. So here we had one solution. Here we have 0 solutions. Zero number of solutions. This is called an inconsistent system. Of course, it's also independent. Lastly, let's look at the case of coincident lines. And so two lines are coincident. So suppose I have this line, L1, and I have this line, L2. So they're both the same lines. So this is both L1 and L2. So here's L1, L2, right? And they're relative to some coordinate system. So this is a case where, well, the slopes are equal and so are the y-intercepts. Again, for the case of vertical lines, that would mean that the x-intercepts were the same. So in this case, I have an infinite number of solutions. As you can see, every point on the line is going to intersect with the other line. So every point on this line is a solution to the system. So every point on the line solves the solution, solves the equation, so solves the system. And so that means that there's going to be, well, a family of solutions, a one parameter family of solutions. So you can take any point along here and you can vary it in one direction. And so this is a one parameter family of solutions. We call this a dependent system. And of course, it's not only dependent, but it's also consistent system. But I usually just call it dependent. Okay, so we can classify a system as either dependent, independent, consistent, inconsistent. Let me do on page 152, problem number 19. Let's call this, let's call it L1. X minus 2y equals 2. Let's call the next one L2. X plus 2y equals 6. In exercises 19 through 42, solve the system of equations by graphing. Identify whether the lines are intersecting, parallel, or coincident. Okay, so let's do that. So first I want to draw what L1 is. So let's determine the slope of L1. So I can solve L1 for y, subtract x, so negative 2y equals negative x plus 2. Divide both sides of my equation by negative 2. And so the negative 2's cancel. So we get y equals negative divided by negative is a positive 1/2 x minus 1. So the slope of this line is 1/2. And the y-intercept is negative 1. Let's actually do it here. Let's determine the slope of line L2. So I have here x plus 2y equals 6. Subtract x from both sides of the equation. So I have 2y equals a negative x plus 6. Divide both sides of my equation by 2. So I have that y equals negative 1/2 x plus 3. And so the slope of this line is going to be negative 1/2. And the y-intercept is 3. Okay, well that's good. That tells me that the slopes are not equal. Therefore, these are intersecting lines, and this tells me that there's going to just be one solution. So let's find that solution. And so let me draw this. Here you're going to have to be fairly careful that you draw this well, because you're going to have to find where these lines intersect. So it's very dependent on how well your graphing skills are. Okay, good enough. So I'm here at -1/2, -1. Okay, so I start at -1. I have a run of 2 and a rise of 1. So that's L1. Next I have 3. So y-intercept of 3, oops, and a slope of -1/2. And so I go over 2, down 1. Okay, now let's draw this. That's L2. Okay, so you just sort of guess where these lines intersect. Somewhere around here. Okay, so my guess is probably somewhere around 4, 1. Don't know. It's a guess. So unfortunately, you don't know where exactly it's intersecting, but you know it's probably something of that order. Uh, and so what I'll do is I'll have to check. So we use the technique that we had from above. I'll just check if 4-1 solves the system. Let's look at L1. X minus 2y, is that equal to 2? Is 4 minus 2 equal to 2? Yes, good. Let's check if 4-1 solves the second equation, L2. And so is x plus 2y equal to 6? Is 4 plus 2 equal to 6? Yes, good. So therefore, the point 4-1 solves the system. So we have determined the solution to this system of equations. Let me do problem number 21. Let's call the first one L1. 4x plus y equals 5. Let's call the second one L2. 3x equals 2y plus 12. Okay, so let's determine the slope of the first line. Let's subtract 4y from both sides of my equation, 4x from both sides of my equation. So y equals negative 4x plus 5. So therefore the slope is negative 4 and the y-intercept is 5. Okay. Next, let's determine the slope of the second line. And so let's solve this for y. Subtract 12 from both sides of my equation. So I have 2y equals 3x minus 12. Divide by 2. So y equals 3 halves x minus 6. So the slope for my second line is 3 halves, and the y-intercept is negative 6. Okay, so I have that these two slopes are not equal. So this is the case of intersecting lines. So that means that there's going to be one solution. So I have a unique solution. So let's do the first one. Ooh, that's really far apart, isn't it? So 1, 2, 3, 4, 5. Okay, so somewhere around here. Okay, let's see if I can do this. Okay. Mm. Okay. Okay. So let's start at 5. 1, 2, 3, 4, 5. Okay. Go over 1 down 4. Okay. That's L1. L2 starts at negative 6. 1, 2. Okay. And then you go over 2 up 3. Okay, so I think it's right there. So my guess is, so this is L2. My guess is that that's at negative 3, positive 2. That's my guess, where that point of intersection is. So let's check. If negative 3, 2 solves the first equation. Ooh, here, wait. Let me just check about the slope. It's up, oh, it's up 3, but over 2. 1, 2, 1, 2, 3. Okay, so let's check that. Okay, 21. Okay, this is 21. Negative 8. Oh, wait, you stupid. 2, negative 3. X is positive. Y is... Okay, so let's check if that's a solution to... I wrote it completely wrong. No wonder. Let's check if 2, negative 3 solves L1. And so is 4x plus y equal to 5? Is 8 minus 3 equal to 5? Yes. Next, let's check if 2, negative 3 solves the second line. So is 3x equal to 2y plus 12? Is 6 equal to 12 minus 6? Yes. And so the unique solution is 2, negative 3. And so this is a consistent independent system. There it is. Okay, so let's do problem number 23. So let's call the first line 2x plus y equals 5. Second line, y equals 3. So let's determine the slope of the first line. So subtract 2x from both sides. And so I get that y equals negative 2x plus 5. So the slope is negative 2, and the y-intercept is 5. Let's look at the second line. Well, the second line is just a line of the equation y equals 3. So that means that this is a horizontal line. Any line of the form y equal b, we said was a horizontal line. So that means that, well, this has a slope of 0 and a y-intercept of 3. And so these slopes are not the same. And so this is the case of intersecting lines. So let's draw. Okay, so the y-intercept is 5. So y-intercept is 5. 1, 2, 3, 4, 5. And the slope of negative 2. So go over 1 down 2. So it should look something like, yeah, well, not a very good graph, but okay. Next, the other one is always y equal 3. Oops. And so 1, 2, 3. Okay. And so L1, L2. I believe the point of intersection is 1, 3. Let's check to see if that really is a solution. Oh, I did label them good. Okay, so let's do that. I still get it. Oh well, doesn't matter. Okay, so let's check. If 1, 3 solves the first equation. This is 23. Is 2x plus y equal to 5? Is 2 plus 3 equal to 5? Yes. Let's check if 1, 3 solves L2. The second equation is y equal to 3. Yes. And so 1, 3 is your solution. Let me do problem 25. Let's call this L1. X minus 2y equals 2. Let's call the next one L2. 2x equals 4y minus 2. Okay, so let me determine the slope of the first line. Subtract x from both sides of my equation. So negative 2y equals negative x plus 2. Divide every term by negative 2. So I get that y equals 1/2 x minus 1. So slope 1/2, y-intercept negative 1. Let's determine the slope and y-intercept for the second line. So you have 2x equals 4y minus 2. Add 2 to both sides of the equation. So I get that 4y equals 2x plus 2. Divide every term here by 4. And so I get that y is equal to 1/2 x plus 1/2. And so the second slope is 1/2, and the y-intercept is 1/2. 25. Yes. Okay. And so the slopes are equal. And the y-intercepts are not the same. Therefore, this is a case of parallel lines. So it means that this is not going to have any solution. Okay, so let me draw the graph. Don't want to draw too much because it's going to be hard to make it parallel. So the y-intercept is -1, and the slope is 1/2. So over 2 up 1. Good enough. That's L1. Next one is at positive 1/2 over 1 up 1. Good enough. That's L2. Okay. And so there's no point of intersection, so this has no solution. Since they're parallel lines. Let me do problem 27. Oops, call it L1. 2x minus 3y equals 4. Call this L2. Y equal -2. Okay. And so, let's look at L1. Well, maybe I'll look at L1 over here. And so I have 2x minus 3y equaling 4. Subtract 2x. So -3y equals -2x plus 4. Divide by -3. And so y, negative divided by negative is positive 2/3 x minus 4/3. So the slope of the first line is 2/3, and the y-intercept is -4/3. Let's look at the second line. Again, this is a horizontal line. its slope is 0, and its y-intercept is -2. And so, in this case, the slopes are not equal. So this is the case of a intersecting line. Okay. Okay, me? Oh, this is going to be hard. Now I can't see the original equation. Okay, so let's draw the graph of this. See if I can make it straight. It's a little crooked. Okay. So let's do this. Keep missing. Okay. Okay, so the y-intercept, so let's do second line. Y-intercept is -2. Okay, so L2. Let's do L1. Y-intercept is, okay, so don't do a y-intercept. Okay, so let's see. Easy point is 2, 0. So let's put 2, 0. So that's a good point. And then I have a slope of 2/3. So over 3 up 2. Okay. So let's draw the line going through those points. Okay. It's L1. So the point of intersection looks like -1, -2. So let's check. Let's see if that's the actual intersecting point. So let's check. If the point -1, -2 solves the first equation. And so this is problem 27. So is 2x minus 3y equal to 4? Is -2 plus 6 equal to 4? Is 6 minus 2 equal to 4? Yes. Let's check. If -1, -2 solves the second equation, L2, and so is y equal to negative 2? Yes. Okay, good. And so, negative 1, negative 2 solves the system. Let's do problem number 29. So let's look at L1. 3x equals 5 minus 2y. Second equation. 3x plus 2y equals 7. Okay, so let's look at the first line. Subtract 5 from both sides of my equation. So 3x minus 5 equals negative 2y. Divide by negative 2. And so y is equal to negative 3 halves x plus 5 halves. So the slope of the first line is negative 3 halves, and the y-intercept is positive 5 halves. Let's look at the second line. Three x plus 2y equals 7. Subtract 3x from both sides of my equation. So 2y equals negative 3x plus 7. Divide both sides of your equation by 2. And so y equals a negative 3 halves x plus 7 halves. And so the second slope is equal to a negative 3 halves, and the y-intercept is equal to 7 halves. And so I have that the slopes are equal, but they're not the same lines. Therefore, this is the case of parallel lines. So I know that this is not going to have a solution. Okay, so 1, 1. Oh, that'll be 1, 2. Okay. Okay, so for the first line, uh, an easy solution is the point 1, 1. That solves it. So let's look at the point 1, 1. And while we go over 2 down 3, draw a line connecting those. Okay. Next, 1, 2 is an easy solution. So 1, 2. Go over 2 down 3. So, Not too bad. Here is the other line, so that's L1, L2. Okay, and so these two lines are parallel, so this has no solution, no point of intersection. Let me do problem 31. X equals 3y minus 1, L2, x equal 2y. Okay, so let's look at L1. X equals 3y minus 1. Add 1 to both sides of your equation. And so I have that 3y equals x plus 1. Divide by 3. So I have that y equals 1/3 x plus 1/3. And so the slope is 1/3 and the y-intercept is 1/3. Look at L2. Divide by 2. So I have that y equals 1/2 x. And so the slope is 1/2 and the y-intercept is 0. And so I have here that the slopes are not the same. So this is a case of intersecting lines. So there'll only be one solution. Not enough room here. Okay, so let's see. For the first line, 1, 2 is a good point. So 1, 2. Oh, 2, 1. 2, 1. Okay, so 2, 1. And you have a slope of 1/3. So over 3, up 1. And so I have good enough. I have here L1, L2, y-intercept is 0. Okay. A slope of 1/2. So over 2, up 1. Okay, so looks like this. So my point of intersection would be 2, 1. Let's check. Well, maybe I'll do part of the check here. Check if 2, 1 solves, let's say L2, because I can do that here. Is 2, is x equal to 2 times y? Well, yes, 2 is equal to 2. 2 is equal to 2 times 1. Let's check. If 2, 1 solves the first equation. Okay, so let's do that. Is x equal to 3y minus 1? Is 2 equal to 3 minus 1? Yes. And so, yes, 2, 1 is a solution. So my solution is the point 2, 1. Let me do, oh, maybe not. Okay, so I guess that finishes off today's lecture. So I guess tomorrow we'll do some more of these, but it'll be at the regular time. So I guess I'll see you tomorrow at 11:15. Hmm. Hmm.